What do a coral reef
and a river delta have in common?
Hi,
We are Bart Peters,
and Femke Meester.
and we're going to have a presentation about diffusion limited aggregation.
Enjoy. So, as you might have guessed, both the coral reef and the river delta are examples of fractals. And actually, both of these and many more things in nature are formed through the same mechanism, which is called diffusion limited aggregation, or DLA in short.
Some things that this type of fractal also makes in nature are, for example, snowflakes, or mountain ranges, blood vessels, or, in certain conditions, bacterial colonies.
So how does this work? We start with a box. This box contains a seed, which is a starting point for fractals. Particles that hit this starting point will stick to it. A seed could be a single point placed somewhere in the box, it could be the edges of the box, or it could be a collection of points. The choice of seed placement and shape will impact your results, but the principle of diffusion limited aggregation is always the same. So for now, we consider one seed particle, which is placed in the center of the box. Then we look at one particle. This could be a bacterium, a molecule, or just something else which diffuses around. This particle diffuses in the box until it hits the seed, and then it sticks. Now we look at another particle which does the same thing. We repeat this process for many particles until a large shape has appeared. What will this look like? You might expect a circle if particles are coming in from all directions. However, this is not exactly what happens. When a particle sticks to the seed, it creates a protrusion to which then other particles can stick. And as diffusion over twice the distance takes 4 times as long, it is much easier for particles to reach these protrusions that are sticking out. So they will extend them. And from such a protrusion, branching can occur as well, when particles stick to the sides instead of the end. And then we get tree-like shapes in all directions, with smaller and smaller branches as you go further outwards from the center. A fractal. Now that you know how DLA works, let's make some fractals. We start with a very simple case, the one that I already briefly mentioned, where we have a box, and in the center of this box we have a seed particle, and every time we simulate one particle diffusing through the space, and when it hits the seed it sticks to it, and when it doesn't it just keeps diffusing until it does, and in this way over time we get a growing aggregate in the center, which you can see over here. Every time particles are sticking to it, it's growing, it's branching. We get smaller branches as we go on, and we create fractals that look like this. Now, we can already see branching here, but it is a bit small. The box is only 100 pixels wide, the particle number is not that high, but sadly this already takes a while to run, to simulate, and so there must be a way to speed this up. And there is, because instead of looking at one particle at a time, we can simulate a whole bunch of particles diffusing through the box all at once and see what happens with that. So that's what we did for another simulation that you can see over here. Just like in the previous one, we have a seed particle in the center over here, in this box that's 10 times larger than the previous one. And all the purple particles in the background that you see are diffusing particles. And when they hit the seeds, they too will stick to it. So let's see what happens. So as you can see, the principle of the fractal is the same as last time, but this one is a lot larger. You can see the branches much better. And for this one, it is also a lot easier to do some calculations, like determine the fractal dimension, which we will do later in this video. Okay, something else that we can simulate with this DLA simulation is that we don't need to limit ourselves to only one seed in the center of the box. We can also look at, for example, what happens when we have a line of seed particles placed at one side of the box. Something you could, for example, see when you're looking at the growth of coral reefs. So for that, we take a look at this simulation, where in the right image you see all the particles present in the box, which will start diffusing, and over here on the sides are a couple of seed particles placed, and that's where the fractals will start growing. So this looks like the following. As you can see, the particles get depleted where the fractal is growing because all of them are aggregating to the fractal, and the fractals start going to the left. And you can sort of see this seaweed or coral-like structure start to appear. And lastly, something else we can simulate with this simulation is the effect of drift. So far, we have assumed that the diffusion is completely random and there is no preference for one direction or another. However, this is not always the case. Sometimes there is a flow, which could happen if you were looking at the formation of a river delta, where of course the water is flowing, and this will have an effect on the branching pattern that you see. So for this last simulation, we have again a couple of seed particles on a line, this time in the center, so we can see the different effect on the left and on the right side a little bit. And over here, all the particles present in this box. And there is a drift in one direction. So let's see what happens. Once again, we see that the particles get depleted, but this time as the particles are all moving to the left, which you can see because they are all assembling here over here, there's a whole buildup of particles because they cannot exit the box on the left side. But on the right side, they all get depleted as the fractal is growing in that direction. So basically, the fractal grows in the opposite direction as the drift of the particles is.
All right, so now that we know how diffusion limited aggregation works, and now that we've seen an example of it for example, a bacterial colony, let's look at another biological example. In this case, our interest went out to blood vessels. We went looking around and we found a paper from 1999 by Vincent Fleury and Fleury and Schwartz, which modeled the formation of blood vessels called angiogenesis as a very different model. It was a model based on shear stresses in the epithelial membrane of these vessels. This brings me to the main point of our investigation, which is how does this model compare to the model that we've just seen? Can both fractals be compared? Let's dive into how this paper models vasculogenesis. We again start with a frame. In this frame, a seed segment in this case is defined. This segment has a starting radius, and the blood running through it has a starting velocity. Together, these create a pressure gradient across the vessel, and with it a shear stress along the epithelial of the vessel. We will assume that these shear stresses do not impede the flow much, but it will become important later on. From the pressure gradient, we can determine the propagation speed of vessel growth, creating a next segment some distance away. The radius tapers with a set decay constant, which will cause the blood inside to flow faster. This flow is given by Bernoulli's equations. This larger flow speed will in turn cause the shear stress to increase, and when the shear stress crosses a critical value, the epithelial will tear. Then, two new directions of flow are chosen at random, and once again using Bernoulli's equations and a few assumptions, the new side branch dimensions can be calculated. Repeat this for a while, and a fractal starts to be formed. So what does this emergent fractal look like? Indeed, if we look at the base, we see a tapering vessel as it propagates. The radius gets smaller and smaller. Then, at a certain point, we see a branch point. This is where the shear has crossed a critical shear threshold. If we then zoom into the next branches, we see that again the same thing is happening. The radius is tapering as the vessel propagates, and then it again branches into two different branches. If we zoom into the really small vessels, then we see that even these still create branches. This thus results in a very fractal-like form. In this model, this creates a large mess of vessels everywhere. But in real life, this would not be the case. In real life, blood vessel propagation is mediated by a compound called VEGF. This would normally be excreted by some kind of target, and the vessels would know that they have to grow in that direction, so they will have a bias. This also happens in some cancer cells. They have a mutation which makes them excrete this VEGF compound, which will cause angiogenesis to be biased towards the cancer tumor. This in turn will make the vessels wrap around the tumor and will make sure that the tumor is properly provided enough oxygen to grow. So keeping this in mind, we now would like to compare our first model of DLA with our second model of angiogenesis. We can do this in a couple of different ways. First of all, by just looking with our eyes, but a more analytical way is to calculate the fractal dimension of both fractals. So how do we again calculate the dimension of a fractal? We use a method called box counting. We talked about it during the lecture, but let me re-explain it a little bit. So say that we have a fractal inside of a frame. We're going to scan this frame with a couple of differently sized boxes. In this case, we drew 2. We save the value for the size of one small box as R, and then we count how many boxes are needed to completely cover the whole fractal. We call this number n. We can then calculate the fractal dimension d by taking the logarithm of both and taking the slope of that fit. Actually, there is a much easier way to do this, and that's using image j. And actually, Femke is doing that right now. Femke, what are you doing?
Hello, welcome. So here we are going to do the thing that Bart just explained, but now we're not going to count the boxes manually, but we'll have image j do that for us. So here we see a fractal that we've created with our algorithm, and we can go to image j fractal box count option, select a couple of different sizes for the boxes we will use to do the box counting, and click OK. And then what we get is this graph with here the logarithm of the box count, so n, and here the logarithm of the box size, r, and the slope of this resulting line is our fractal dimension, which, as you can see, is around 1.5 for this fractal.
When going through the same procedure for the angiogenesis model, we eventually find that the emerging fractal has a dimension of around 1.35. When comparing this to the fractal dimension found for the typical DLA model, we notice that this is quite a bit lower. This is at least an indication that the two models are not identical. But I did mention another method to compare them earlier, using our eyes to see what is happening. When putting the two emergent fractals side by side, it's clear to see why one fractal dimension is lower. Where the normal DLA model seems to produce a more solid fractal with a relatively large area, the blood vessel fractal produces a mess of string-like objects which more closely resembles a one-dimensional system. Another observation that can be made is that the DLA model seems to have more directionality to it, whereas after a certain number of branch points, the blood vessels seem to go in arbitrary direction where crossing is allowed. Nevertheless, it's really cool to see that these two seemingly unrelated models could produce such similarly looking patterns.
So, for both of the models, the angiogenesis and the simple DLA models, we see some similarities. For example, that for both of the resulting fractals, you see smaller and smaller branches as you simulate for longer and as you go further away from the seed point. This also means that for longer simulation times, the fraction dimension will go up as well. So this is important to keep in mind for the numbers we calculated as the fraction dimension, fractal dimension.
When looking at this fractal dimension, we see that they are very close in magnitude. This means that most likely the fractals can be compared, but are not strictly identical. In any case, it's really nice to see that two such different algorithms or two such different models can lead to a very similar fractal. We really hope that you learned much about these kinds of fractals in nature and that you can really appreciate the beauty of seeing them from now on. And we hope that you keep on diffusing